Alright, so I'll put the first function, x squared minus 6, and then I need to open parentheses again, hit x, then second math, I want less than or equal to, which is 6, and that's going to be less than or equal to 3, plus the second function, open parentheses, 2x minus 3, close them, set it up like a multiplication problem, x, second math, and this time we want greater than, which is 3. You could also arrow down, and then 3 is the endpoint. Close it. And again, I'll start with a zoom 6, and then I will alter it as I need to. Alright, so this function we actually get, we get a decent idea. We can see the parabola, that is the top function, x squared minus 6. The bottom function is a linear equation, and it does seem to me that you can see here that it looks as if there's no gap in the equation. At that endpoint, if we trace on, let's trace on the 3. So depending on how you do this, you know, on a test, generally you're going to be given these on a non-calculated part of a test. But when you're doing your homework and you're practicing, you can either graph the function first and confirm it with your analytical work, or do your analytical work and check it with the graph. But you can see here that at x equals 3, it certainly appears that both functions have the same exact value, and so this is continuous everywhere. Alright, let's look at example C. We've got f of x equals 1 over x if x is less than or equal to -1, and x if x is greater than or equal to -1. We start off by focusing on the individual functions, and I know that the top function, 1 over x, that's continuous as long as x doesn't equal 0, and since we're only using this function for values of x that are less than -1, then 0 is not going to be an issue for 1 over x. The portion of this function that we're using does not include 0. So this would be continuous on this given interval. Okay, and then the function x is a linear function. That's continuous everywhere. So right now, again, our only issue is the issue of the -1, and so we'll look at the limit. So the limit as x approaches -1 from the left, we'll be using, that's the same thing as taking the limit as x approaches -1 of 1 over x. So when we plug that in, we're going to get -1. The limit as x approaches -1 from the right of f of x, we're going to use the function x, and so that's also going to be -1. And f of -1 is the same as this limit. It's going to be -1. So this function, even though 1 over x would have had a discontinuity at x equals 0, since we're not using that function on an interval that contains 0, then that portion of the function is continuous. The portion of f of x equals x is continuous, and also we are continuous at x equals -1. So the interval of continuity on this is basically all real numbers, or we would say this function is continuous everywhere. And I think it's a good idea for you to also, you know, try this on your graphing calculator and see how it looks. So I put each of these functions in my y1 with their given intervals, and I started with a zoom 6, and then I just zoomed in once. So we get a nice picture here. There's a portion of the 1 over x graph with the linear function. Let's go on to the next problem, where they're not asking us for the interval of continuity. They're just asking us to find out if the function is continuous at x equals 1. And so in order to determine whether a function is continuous at a point, we use the continuity checklist. So this function, we've got x squared minus 1 over x minus 1, which is this is the function that we're using for all values of x except x does not equal 1. And so we want to find the limit as x approaches 1 from the left and as x approaches 1 from the right. When we plug in a 1, we get 0 over 0. So we know we need to do more work. So we'll factor x plus 1 times x minus 1 over x minus 1. The x minus 1's cancel, and now when we substitute in, we just get 1 plus 1, which is equal to 2. So because this is a rational function, and once I've substituted in the value of 1, the limit from the left and from the right are actually going to be exactly the same. They're both going to be 2. Now, f of 1, well, that's 3, because it says here the function is equal to 3 as long as x equals 1. So f of 1 is equal to 3. So in this case, the function is not continuous. Right, so this function is not continuous at 1. So what this graph actually looks like, even though this is a rational function, when you graph it on a calculator, you'll see just a line. And the reason is that once you cancel that common factor out, all that's left, when you cancel that common factor out, all that's left is the function f of x equals x plus 1. And so that common factor just creates a hole in the graph at 1. So right here, at over 1 up 2, you have a hole in the graph. The limit equals 2, but the function value actually equals 3. So you have this ordered pair up here. So this is what this function actually looks like. And so you have a point of discontinuity at x equals 1. I want you to pause the video and then determine the intervals of continuity for the following functions. Do this without a calculator. If you want to, try to graph the piecewise on your calculator when you're done, that's okay, but try to answer the questions without the use of a calculator. And then start the video up again to check your work. Alright, so the first one is a polynomial function, and polynomial functions are continuous everywhere. So the interval of continuity is just negative infinity to positive infinity. Number 2, we start off with the original function, and the only point of discontinuity, if we look at the functions as standalone, the only place where this rational function would be discontinuous is when x doesn't equal 3. And since we're only using this function for values of x such that x does not equal 3, then this function is fine. And then the next function, f of x equals 2, that's continuous everywhere, and we're only using that for x equals 3. So the only thing we need to test here is what's happening at x equals 3. So the limit as x approaches 3 from the left and the limit as x approaches 3 from the right, both of those we'll be using this function. And so we would just evaluate the function at 3. So 3 squared minus 4 times 3 plus 3 all over 3 minus 3. That would give us 0 over 0, in which case we know that we need to factor. So we'll get x minus 3. So we want to take the limit as x approaches 3. The x minus 3 will cancel, and we can now plug in the 3. We get 3 minus 1, which is 2. So we know the limit is equal to 2. So we've got the limit is equal to 2, and f of 3 is equal to 2. Right? So if the limit exists and the function value exists and they're equal to each other, then we are continuous at that point. So we know we're continuous everywhere. F of 2 is continuous everywhere. The x squared minus 4x plus 3 over x minus 3 is continuous everywhere but x equals 3. And then when we test x equals 3, we have continuity there also. The interval of continuity is from negative infinity to positive infinity. All right, for the next function, it's not a piecewise, it's just a rational function. So I want to first find out where there are any asymptotes or any holes, because a rational function is continuous everywhere in its domain. Our job is to find those values that are not in its domain. So in this function, the values that are not in the domain are the values for which the denominator is equal to 0. So we know that t cannot equal -1, t cannot equal 1. At positive 1 we would get a hole, even though they're not asking us right now to do that. That we're just I'm just kind of elaborating here. And at t equals -1 we'd have a vertical asymptote. But our intervals of continuity would be from negative infinity up to -1, union -1 to 1, and then 1 to infinity. Basically setting this up so that we exclude -1 and 1.